Hi, welcome to Chapter 16, Acid-Base Equilibria Overview Part 2, where we're going to talk about strong acids and bases, weak acids, and weak bases. Strong acids, if you remember from over the summer, we talked a little bit about strong acids, and they are acids that completely ionize. They ionize 100%. And there are a few of them that do this, which are listed here. There are 7 of them. And over the summer, I suggested that you memorize them. So I would memorize these 7 strong acids. Okay? By definition, a strong acid is a strong electrolyte, and they exist totally as ions in an aqueous solution. So here is a binary strong acid plus water, and you're completely breaking up into all the ions. Notice the one-way arrow, meaning that this reaction goes to completion. 100% of it ionizes. So if you have a monoprotic strong acid, that just this monoprotic means the one hydrogen here, your concentration of hydronium is equal to the concentration of the acid. So for example, if you have 0.1 molar HCl, that means your concentration of hydronium is 0.1 molar. Strong bases dissociate 100%. So the strong bases are your group 1 metals that are bonded with hydroxide, and only these 3 from group 2. So again, I would memorize your strong bases. Okay, there aren't that many of them. And they completely dissociate. So if you look here, you have your group 1 metal with hydroxide breaking up into the metal ion plus OH minus. And your group 2, just the 3 of them, calcium, strontium, and barium, doing this. Notice the one-way arrow again because it 100% dissociates. Now, interestingly, the group 2 metals will dissociate 100%, but their solubilities are very low. So you can't dissolve a lot of, say, barium hydroxide in water. A weak acid. So if a strong acid ionizes 100%, a weak acid does not ionize 100%. Okay, so now instead of having an arrow pointing in one direction, we have a reversible reaction. We establish an equilibrium because the photoreaction will occur when it's ionizing, and then the reverse reaction will occur when you're forming just your HA acid here. Okay, and if we wanted to write our equilibrium constant for this, remember it's your products. So what we learned in chapter 15, still here, divided by your reactants. And water is pure, so it's not in your equilibrium. And since this is for acids, we put a little a here. So we call this Ka, or your acid dissociation constant. The larger your Ka, the stronger your acid. Okay, stronger the acid. Because, think about it, the more of your acid that ionizes, you're going to go forward more, you're going to make more products, so the top will be larger. So you have a larger value of Ka. So let's compare strong and weak. What is present in solution in a strong acid versus a weak acid? In a strong acid, you have all ions, right? Your acid separates into ions completely. In your weak acid, it only partially dissociates, partially. So you will still have some of your original acid in there. So another comparison between strong and weak acids. In a strong acid, your hydronium or H plus concentration will equal the concentration of your acid. In a weak acid, this concentration here, your hydronium or H plus, will be less than your initial concentration of your acid. Remember, because not all of it will ionize. So this also creates a difference in conductivity and the rates of the reaction. So your strong acids will react faster than your weak ones. So how do we calculate Ka from the pH? So here we have an example. We have the pH of a 0.1 molar solution of formic acid, which is a weak acid. Here is the formula for it. It's not one of the 7 that you memorized. And it's at 25 degrees Celsius. And the pH is equal to 2.38. Calculate Ka for the formic acid at this temperature. So the first thing you always want to write down is your equation. So you have your formic acid plus water making your hydronium plus this ion right here. Then write your Ka, products over reactants. Now to calculate Ka, we need the equilibrium concentration of all 3 of these. Okay, and what information did they give us? They gave us pH, right? So we could find the concentration of hydronium using the pH, which is the same as this ion here, right? Because all these ratios are 1. So remember, pH is equal to the negative log of your hydronium. And if that is equal to a number, right, say you want to do the opposite, we call that the anti-log. You take 10 raised to the negative, this negative number here, whatever your number is. Okay, and that will give you the concentration of hydronium, and that's called the anti-log. So that's what we're doing here. 10 raised to the negative pH value. There are 2 decimals on my pH, so I have 2 significant figures. So this is the concentration of hydronium and of the formate ion. Okay, so now let's do our ice table. So we know our initial concentration of formic acid, and these 2 are 0. We know at equilibrium the concentration of formate and hydronium. So we can figure out the change that occurred here. These are increasing, so this has to decrease. So we take our initial concentration minus this 4.2. Now notice, with significant figures, when you're adding or subtracting, you round to the least number of decimal places, which is 2. So we have to round this to 2 decimal places. So this 5 will make this round up to. So really, was subtracting this value relevant? No. So we could ignore that because of significant figures. So now we put all our concentration values in and we get our Ka. We could also calculate the percent of our acid that ionizes by taking the concentration of hydronium over our initial concentration. You see here it is 4.2%. Okay, and what does the percent ionization tell you? It tells you how much your weak acid ionized. So only 4.2% of it ionized. Okay, why do we not take into consideration the autoionization of water, right? Just water at 25 degrees C will have a hydronium concentration of 10 to the minus 7. Because this 10 to the minus 7 is significantly less than this 10 to the minus 3. So with using our significant digits and all that, it really will not affect our data. Unless we have a concentration of an acid that is on the same order of magnitude, we do not have to worry about the autoionization of water. So the method for calculating pH using Ka. 1, we write the chemical equation and the ionization for ionization equilibrium. Then we write our Ka. Then we set up our ice table, and then we plug in all the values that we know and make assumptions if you can. So let's work through this. So let's calculate the pH of a weak acid. So we want the pH of 0.3 molar solution of acetic acid. So the first step is write the equation. Acetic acid plus water will make hydronium plus acetate. Then write your Ka value. Then do your ice table. What do we know? We initially started at 0.30 moles of acetic acid. 0 moles of hydronium and acetate. Okay, we know the reaction has to move forward because we have zeros here. So these will increase by some value x, and this will decrease by some value x. Typical ice table. Okay, now we plug them into our Ka. So what do we end up with? X squared over 0.3 minus x. Now, if you remember in our previous example, when we subtracted that 4.2 value from 0.1, it was 4.2 times 10 to the minus, I forget what it was, 4 or 7 or something like that. It really had no significance, right? Because it was beyond our 2 decimal places significant value. So we were able to ignore that. So what am I saying? I'm saying that when you get these situations like this, you can ignore the x that you're subtracting because it's so small that when you round to significant digits, you're going to end up with 0.30 anyway. Okay, so you end up with this relationship and you set it to the value of your Ka. Most of these Ka values can be looked up on data tables. Then you could rearrange this and solve for x. X, remember what was on top here, it's the concentration of hydronium and acetate. So x will be the concentration of your hydronium, which is also the concentration of your acetate. But we don't really care about the acetate. The hydronium is what we need to get our pH. So when we do that, we get that x is equal to 2.3 times 10 to the minus 3. So in order to get the pH, you take the negative log of your hydronium concentration. And there are 2 sig figs here, so you'll have 2 decimal places for your pH. Way different than just taking the negative log of 0.3, okay? We also have acids that have more than one hydrogen in them. When they have more than one hydrogen, we call that polyprotic. This product means protons, poly means more. So these polyprotic, I'm not sure if I'm actually pronouncing that correctly, acids have more than one acidic proton. What you need to know is that the first hydrogen that you remove, the first proton, is the easiest to remove. Okay, so it will have, the first one will have a larger Ka value, and we call that Ka1 for the first one. So Ka1 is always greater than Ka2, which is always greater than Ka3, so on and so forth. Okay, and why is that? Well, once you lose, so let's take carbonic acid. Once you lose one, okay, if I just rip that apart right here for conversation. Let me reset this. Messy. So here we lost the proton. Now it has a negative charge on it. Because this is now negative, it's going to hold on to this last proton, the positive hydrogen, a little bit tighter. So it's harder for it to dissociate. So that is why Ka2 is less than Ka1. And if you look here, Ka1 for carbonic acid is 4.3 times 10 to the minus 7. Ka2 is more than 3 orders of magnitude difference. Okay, so if the factor of Ka values for the first and second dissociation have a difference of 3 or greater, so this went from negative 7 to negative 11, so that's greater than 3. The pH generally only depends on the first dissociation, so you can kind of assume only the first one is controlling the pH. If the difference between the first and the second is less than 3, then you have to worry about the second one. And when I say 3, I mean if you're looking at the exponents in the Ka values. Well, if there's a weak acid, there's also a weak base. And if a weak acid does not ionize 100%, a weak base does not dissociate 100%. So we need to set up an equilibrium expression where we have the double arrow. Here B is our base reacting with water. We end up with BH, because remember, the proton gets donated to the base, and OH minus. Bases react with water to produce a hydroxide ion, okay? So our Kb, B for base, here is your product concentrations over your reactants. Again, water is not in it because it's pure. Just as the larger Ka means a stronger acid, the larger the Kb value, the stronger the base. Just means that you're going forward more, which means that you're dissociating more, which means that you are stronger. So here's an example of a weak base, probably the most famous one, ammonia. So you have ammonia plus water making NH4, ammonium plus OH minus. And going back to our Bronsted-Lowry, you have your base with its conjugate acid, you have your acid with its conjugate base. So like weak acids and weak bases have an equilibrium constant called the base dissociation constant, and that is Kb. Equilibrium concentrations work the same as what we just did for the acids. We'll go over an example in a minute. So many bases contain nitrogen as an element due to the lone pair that is on nitrogen, right? This has a lone pair of electrons that can attract the proton. Remember the proton from water. These electrons are going to attract it. And that's why they're a base. Bases that have nitrogen in them are called amines. If you take organic chem, you'll learn a little bit more about that. So two main categories of bases. You could have neutral substances with an atom that has a non-bonding pair of electrons. So just like NH3. Or you could have the anion of a weak acid, okay, which are their conjugate bases. Those are your two types. And here are some typical Kb values, okay, and we could use Kb to find the concentration of hydroxide, and through that pH. So let's do an example. Calculate the pH of a weak base. So here we have what is the pH of 0.15 molar NH3? So we write our reaction. We write our Kb. You can look up the Kb value in data tables. Then we fill out our ice table. We know we started with 0.15 and we had 0 of each of these. So these are going to increase by a value of x, and we're going to subtract x here. Now, again, this subtraction of the x, this x is going to be much smaller than our initial concentration. So we could ignore this x right here. And that is only true if x is much smaller than the initial concentration. So again, we end up with x squared over 0.15 minus x is equal to 1.5 times 1.8 times 10 to the minus 5. We can ignore this x, so we end up with x squared over 0.15 equals 1.8 times 10 to the minus 5. We can multiply, take the square root, solve for x, and we get that x is 1.6 times 10 to the minus 3, which is smaller than 0.15, especially when we're doing significant figures, right? If I wrote this out longwise, this has, and we're subtracting, so we're going to round to the least number of decimal places, which would be here. So this would have no effect on the concentration of our first compound there. So what did we just calculate? We calculated x, But what was X? X was the concentration of hydroxide. And we are looking for pH, right? So there's two ways you could do this. One, you could take the negative log of this, and that'll give you POH. And then you do 14 minus POH, and that would give you your pH. The other way is you can remember that hydronium times hydroxide equals 10 to the minus 14, and you could solve for hydronium by plugging in the hydroxide concentration. This way is a little bit harder, this way here. This way is a little bit easier. You're not working with all these exponents and all that. So let's try this last example in our video for today. So you have a solution made by adding solid sodium hypochlorite, which is NaClO, hypochlorite, sorry, to enough water to make a 2-liter solution. This 2 liters is important. We'll come back to that later. It has a pH of 10.50. Calculate the number of moles of sodium hypochlorite that were added to the water. Okay. So what do we do first? So we have our reaction. We have our Kb value. Remember, Kb is just going to be equal to okay, and they gave us the pH. What could we get from the pH? The pH can give us hydronium, but we have hydroxide here. Well, luckily, your POH is 14 minus your pH. So when you subtract the two, you're going to get 3.50. By taking the anti-log of your POH, you get 10 raised to the negative 3.50, and that's going to be our concentration of hydroxide, which is equal to, when you punch it in your calculator, 3.2 times 10 to the negative 4. 2 decimals, 2 sig figs. Okay. So now we know the concentration of hydroxide. Let's set up our ice table. So initially, we don't know what we have. That's what we want to solve for. We know we had 0 of each of these. Okay? But what we do know is at equilibrium, we have 3.2 times 10 to the minus 4. And if you look here, these mole ratios are 1 to 1, so the concentration of hydroxide is the same as for this ion here. So we have this. So that means if this side is getting added, this side must be getting subtracted. Okay, so now we know our equilibrium concentrations with our X here. We want to solve for X, so we plug it into Kb. Kb is the concentration of HClO, which is 3.2 times 10 to the minus 4 times the concentration of hydroxide divided by the concentration of our hypochlorite, which is X minus 3.2 times 10 to the minus 4. And all of that is equal to the Kb value, which they gave us in the problem. Okay, so if we rewrite this, since these two are the same, we are just effectively squaring it. Now if we divide both sides, this is a 3. And that, so we get and then we bring this term over here, so we add that. That's going to equal our x. And when you punch all that in your calculator, that you get that x is equal to 0.31 molar. ClO minus. This is the formula for sodium hypochlorite. So when it dissolves, it breaks up into this, and there's a 1-to-1 mole ratio. So this 0.31 of the hypochlorite is the concentration of your sodium hypochlorite. But what was it asking? Moles. And remember I said this volume is going to come back. So if we multiply this by the volume, we will get our moles of sodium chloride, hypochlorite that was added. Okay, and that is the end of part 2. So rewatch this solving a couple times so you get comfortable with it. We're going to do some practice problems, so don't worry about it.